Let us take up a plane truss problem. It's a plane truss, as I defined already. Here the truss consists of line elements arranged in the form of triangles, all members lying in one plane, and all members are interconnected by pin joint. That is known. And also one more thing, all loads will be acting only at the joints. There is no member load. So no question of finding fixed end moment and all those things. That step is not here, because all loads in analysis of truss, it has to be, loads should be acting only at the joint. The moment load acts on the member, it is subjected to bending. So truss members are not supposed to they are subjected to any bending at all, because joints or ends are pinned. Pinned ends means it cannot transfer or transfer the moment to the support. So no question of any member load. That's another point you have to remember. All loads should be always acting at the joint. Straight away you can use this load, because straight away the load given is in the global direction. So I will select, of course afterwards I will select PD will be in the x direction, it is 10, this is minus 20 in the y direction. So I will select a typical global coordinate to start with. This is the truss given, truss, and I will select a global coordinate. This as x coordinate, this as y coordinate, and I will call the member joints as 1, 2, 3, 4. These are the joints of the truss, and with respect to this coordinate system, the coordinates here, coordinate of point 1, it is x coordinate is 3, y coordinate is 0. With respect to this coordinate system, this is the origin. Here x coordinate is 0 for the point 2, y coordinate is 4, here x coordinate is 3, y coordinate 4, here x coordinate is 6, y coordinate is 4. I will determine the coordinates of the point, and this, for this particular member I will call it as 1, this as member 2, this as member 3. This is the information which I have with respect to global coordinate. Now I will define local coordinate. Local coordinate is always near end. I will take joint 1 as the near end for all the members. That is Jn for all members, 3 members. I will take Jn as 1. Kn will be other ends. So that is J to K. This is our local member axis for the member 1. For member 2, this 1 to 3 is the local axis. For this member 3, 1 to 4 is the local axis. I have defined both global local axis here itself. This is coordinates selected, both local as well as global, for this particular analysis. Knowing this, I will define the load, external load. In global coordinates only we have to take. In global coordinate, chosen that coordinate as the x direction. This is acting in the x direction, so plus 10. So this load acts in the direction opposite to y-axis. That's why I have attached minus 20. This is the PD external load matrix. That is the first thing. Then I have to prepare what is known as joint information. This is the first step. All these, whatever I am telling, they are all first step. All this, including all element properties, what I am determining, they are all first step you can consider. So joint information, I will write in the form of table. I will write joint. There are 4 joints, 1, 2, 3, and 4. 4 joints are there, and coordinates of these joints with respect to coordinates chosen. 2, 2 coordinates because it is a plane truss. So plane figure, it will have only two coordinates. Z will not come into picture and moment is also not there. For joint one, x coordinate is 3, y coordinate is 0. This is in meters. Similarly for 2, it is 0, 4. For 3, it is 3 and 4. For 4, it is 6 and 4. This much information first we have to do. Then we have to find member information. Why we have to determine this member information means all the element stiffness matrix Km that I have to determine based on this. Similarly, global Km, global stiffness matrix, for that also I have to determine L and M, that is the member information. I will prepare a table like this. I will write member. So there are only 3 members. I will write those members 1, 2 and 3. All the 3 members. Here Jn, that is near n. Jn means near n. Jn or near n. Kn or for n. That also I have to determine, because L and M by determining direction cosines. This is very, very important. From which direction we are moving, local coordinate I am defining. This is very, very important thing. If you do mistake here, it is gone, plus or minus. So here for member 1, I have already indicated Jn is 1. For all these members, Jn is 1, already I have told. Kn, for member 1, it is 2. For member 2, it is 3. For member 4, that is for n is 4. Then I will determine Jn, Kn, I will determine directly L. So here I will say L is equal to square root of xk minus xj whole square plus yk minus yj whole square. So for the member 1, xk means x2, x2 minus x1. x2 minus x1 means 0 minus 3. It is minus 3 minus 3 square, 9. Similarly, yk minus yj means y2 minus y1. It is 4 minus 0 whole square, 4 square. So 3 square plus 4 square, that is 9 plus 16, 25. Square root of that is 5. So L is 5 here in meters. Similarly, for 2, it is 1 and 3. Kn is 3. So xk minus x1. 3 minus 3, 0. 4 minus 0 is 4. So this is 0. Square root of 0 plus square root 4 square, that is square root of 16, that is 4 itself. Similarly, this is, you will get 5. This is how the element property length has been defined. A is constant, otherwise you can open out one more column. A is different, then you can find out if they give area of cross section separately. E is also given, then you can work out that AE in same units. You have to work out and write. Here it is AE, AE, AE. Then I have to work out N, which is nothing but xk minus xj divided by N. Direction cosine of the first member. It is xk minus xj. xk means x2. xj means x1. x2 minus x1, right? 0 minus 3, minus 3. Minus 3 divided by 5, it is minus 0.6. Then for this, L is x3 minus x1, that is 3 minus 3, 0. So L is 0 because it is vertical member, naturally L will be 0. That you can observe. The Km matrix will be 1 minus 1 minus 1, 1, 1, 3 will be for this, because it is coinciding with in the orthogonal direction now. So it altogether the transformation need not be done. So that you can verify. So here 3, it is x4 minus x1, that is 6 minus 3. 3 divided by 5, it is plus 0.6. Then my m is equal to yk minus yj divided by n. That is direction cosine with respect to m. So that is yk minus yj, that is y2 minus y1. 4 minus 0, 4 divided by 5, it is 0.8. Here it is next number 4 minus 0, 4 divided by length 4, it is 1. Direction cosine for the vertical member is 1. Here direction cosine m. Here it is y4 minus y1. y4 minus y1. 4 minus 0, 4 divided by 5, it is 0.8. So this is L and M of all the members. That's all the information we need. So now this is first PD I have generated, then PD matrix, then D which we have to determine, or the degrees of freedom also I can write it, that is kinematic independency, what you have done in earlier problems. So here at any joint you can have only 2 types of displacement, no moment. So this 1 and 2, you can always start with the joint where all displacements are possible. So that you can number first 1 and 2. Here no displacement possible because it is support, fixed support. Here it is 0, 0. Here also it is 0, 0. Here also it is 0, 0. Therefore, unknown joint displacements are D1 and D2. That's what the first step we were doing in earlier problems. Unknown joint displacements, unknown member forces. Instead of unknown member forces, I am determining all these member properties. From this, I will determine the element property. So this is B matrix I have generated, PD matrix I have generated here. That PMF and all those things is not there. Only PM, the force in members, that I have to determine, that I will write it. The PM matrix is nothing but, because only one force per member. Assumed direction I have taken like this to start with, positive direction. So this is PM1 I have to determine, PM2 I have to determine, PM3 I have to determine whether it is in the same direction or in opposite direction, whether it is tension or compression, that I have to determine. This is your first step which you have to perform.
So that PM depends on given number of members.
Only naturally only one force, one axial force per member. There are 3 members, 3. Though I have indicated here in local coordinates 2 forces at the 2 ends. 2 ends. That is what we are going to get in our analysis. At the 2 ends only we will get that. From that I have to get actual along the member axis. Along the member I will get a force here, I will get a force from the analysis. That opposite to that, because it is acting outside, opposite to these forces, I have to indicate it. It will be either indicates either tension or compression. That will be the force PM1 and all. That I will indicate in the next third step of my analysis. So next we will go to second step. So what are the calculations which I have done here? There are minor things, nothing extraordinary here. So even in second step also, using this only we are generating nothing other than that. Only in the last step we have some calculation. In second step, we have to generate to find Km and Ks. Global as well as member stiffness matrix for this. So Km, of course, for all the members, it is Je by L into 1 minus 1 minus 1. That is known. Ke by L of all members. Any member, whether I is equal to 1, 2, 3. For all these members, with reference to this coordinate 1 to this, I will call Jn, Kn near n, first coordinate, for n, second coordinate, that you should not forget, always you have to remember. So for any member, this in the terms of JK, 2 degrees of freedom, this is the member stiffness matrix, and L is of course length. That you know, length from this particular table. That you can generate without any problem. Member stiffness matrix, Km1 is AE by 5. Length is 5. AE by 5, 1 minus 1 minus 1. And Km2, it is AE by 4, 1 minus 1 minus 1, 1. For member 3, AE by 5 again, 1 minus 1 minus 1, 1. I have given general expression with respect to these coordinate fusion. That is, you need not do any calculation. Only you have to do this KS. I have to do. KS already I have defined. It is given by AE by L, L square, LM minus L square minus LM. This is symmetric. Then M square minus LM minus M square. This is also symmetric. Then this is L square, LM, LM. This is M square. So these are the things. So this I have to generate for first member 1, 2. This I can call it as the 3, 4, 5, 6, 7, 8. They are zero displacement, but coordinate directions are that. So K1 I have to generate for first member KS1. First thing is AE by L. L is 5 meters. AE by 5. L square. L is 0.6. Of course, we can find those values also here in the table. L square, LM, M square, and straight away you can use it in the formula. L square is 0.36. LM is 0.48. M square is 0.64. Here it is L square 0, LM 0, M square 1. Here it is 0.36, L square, LM 0.48, M square is 0.64. I have determined those for each element. You can substitute and write that KS, global stiffness matrix. Member stiffness matrix, known global also I will determine. For member 1, it is AE by 5, L square is for member 1, 0.36, then LM 0.48, then minus L square, minus 0.36, then minus LM minus 0.48. So this is symmetric, 0.48 minus 0.36 minus 0.48. Then M squared is 0.64. Then minus LM means
minus
it is
0.48.
minus 0.48. Okay, minus 0.48. Then it is minus M squared.
Minus
it is 0.6 minus 0.64. Then here it is minus 0.48 minus 0.64. Then L squared is 0.36. L squared is 0.36. LM is 0.48. So this has to be 0.48. So then now this is M squared is 0.64. These are with respect to coordinates 1, 2, 3, 4 for element 1. 1, 2, 3, 4. 1, 2, 3, 4. You can write that corresponding coordinates. Write global displacement coordinate. Corresponding to that, we have this. Then KH2, you can find out for the element 2, it is AE by 4. Length is 4. L squared is 0. LM 0. Minus L squared 0. 0. All are 0.
So 1 minus M square.
Yes?
Minus M square 1.
That is M square.
M square.
Where is M squared is here?
Yes. No.
There is no M squared in the first row. All are 0. That carefully you have to substitute. Next, it is Lm, of course this side right
0.
0, 0, 0 because it has to be symmetric. Then this element is m square.
One.
Here you are getting
1.
1 minus Lm 0. Then minus m square minus 1. See 1 minus 1 of that local thing itself because it coincides now. That's the reason why in beams and frames you are matching that stiffness matrix. We didn't separate like this, global and local and all. Here we have to separate it. It is the different approach. That's called element approach. Then here also it is 0 minus 1. Then this is L square 0, Ln 0. It is 0 here. Here it is m square 1. So this is for member 2. Then lastly, you can generate the global stiffness matrix for element 3. That is also AE by 5. So these coordinates you can write 1, 2, there it is 3, 4, 5, 6. 5, 6. 1, 2, 5, 6. 1, 2 I am writing here. For this 3, 4, for this 5, 6, for this 7, 8. So here it is 1, 2, 7, 8. 1, 2, 7, 8. You can fill it up. So for this it is L square 0.36. Then Lm is also 0.48. Then minus L square. Minus L square is minus 0.36. It is same, is it?
Yes, sir.
No. Here it is, I have not written. It is minus 0.48. Because L into M, it is minus 0.48. So here, Lm, minus Lm is okay. This is
Plus 0.48.
plus 0.48. And similarly here, it is plus 0.48. Then in this it is minus, so it is plus 0.48. Here also it is plus 0.48. Here it is Lm minus 0.48. Here it is minus 0.48. Whereas here it is plus.
Yes.
That you have to be careful. Anything you can see here itself, there is no botheration at all. So this is 0.48. Lm minus L square is minus 0.36. Then minus Lm means minus 0.48. So it is 0.48 minus 0.36 minus 0.48. Then we have m squared. M squared is 0.64. 0.64. Then minus Lm minus 0.48. Then minus m squared minus 0.64. Then same thing here, minus 0.48 minus 0.64. Then here it is L square 0.36, Lm 0.48. This is also 0.48. Then m squared is 0.64. These are the elements of global stiffness matrix for the member 3. So having determined this, these are all from whatever just I have derived previous just now. Km I have defined, Ks also I have derived using this expression. I have to determine this. Then you generate K, that is stiffness matrix for with respect to unknown displacement. I am calling it as K, not as only K. That K is nothing but a matrix with respect to 1, 2 only, because there are 2 degrees of freedom. So with respect to 1, 2 only, that 1, 2 only we have to take here. The remaining things, the overall structure stiffness matrix is a big matrix. It is 8 by 8 matrix in this case. 1, 2, 3, 4, 5, 6, 7, 8, all these things of the all elements we have to club together. In this case, if you generate, that will be a big matrix consisting of 1 to 8 elements. Out of that, the while partition I will take only the elements corresponding to unknown displacement. That is 1, 2 only unknown displacement. That only I will take it. I have not generated the overall structure stiffness matrix totally for the structure as a whole. For the stiffness, this is for elements, individual elements. For total structure, I have to club all these and generate it. In that global stiffness, I have to take out only the elements corresponding to unknown displacement. That's why I told you in the beginning, while naming, to number those coordinates for which we have to determine unknown displacement first, 1, 2, so that I can take out those elements easily, as I have written here 1, 1, 2, 2. Here also all the other elements you need not determine, that I am not using in the computation. Only 1, 2, 1, 2, 1, 2, 1, 2 I can write. Remaining things simply I can leave it blank. That is also you can do it. But of course here, since it is small problem, I have done everything. So here it is 1, 1. You take from all the elements. 1, 1, 0.36, then 1, 1, 0, then 1, 1, 0.36. All are AE by 5. Here it is 0. So AE by 5, I will take it outside. That you have to be careful. Here they are different. Otherwise, this you have to take it inside and do that. So that carefully you have to do. I will take straight away AE by 5 here. 0.36, 0.36. It is 0.72. Then 1, 2. 1, 2 here it is 0.48. Here it is 0. Here it is plus. Is it plus or here it is minus, I think.
LM. Minus point.
Minus. It is minus 0.48 plus 0.48. It is 0. Then 2, 1. 2, 1 is this. 2, 1. 0.48. 2, 1. Here also it has to be minus 0.48. Here it is minus 0.48.
Yes, sir. 0.
So it is also 0. Then 2, 2. 2, 2 is 0.64. Then here
1.
2, 2 is 1. This minding I have taken AE by 5 outside. So this I will multiply by 5 divided by 4. So 5 by 4. So it is 1 into 5 by 4.
1 into 5 by 4.
Correct? Huh?
Yes, sir.
So it is 1 into 5 by 4 into 1. That is 1.25. That is 2, 2. And also I add 0.64, 0.64. And write it here from the first element 0.64. Second element, that is 5 by 4, it is 1.25. From here 0.64. If I add this 1.53. This is the right. This you have to do correct. So I have generated KD. Then we have, we can use straight away PD, force displacement relationship, K into D. D is the major unknown force,
D1,
D2. PD, it is given, external node is known, external displacement to be determined. Here I have generated global stiffness matrix. All are in global direction. So I will write this 10 minus 20 is equal to AE by 5, D is 0.7, K is 0.72, 0, 0, 1.53. This D is nothing but D1 and D2. That will be determined. Therefore, D1, D2 is equal to
so
this.
That 1.53 is a 2.53, sir.
2, okay. So 2.5.
Yes.
Okay, this is 5 by AE into determinant of this. You can find out. I will use that straight away. 1.8216. 1 over 1.8216, you can cross check. 0.72 into 2.53, that will be 1.8216 minus 0. that's the determinant, into this. I will leave this point column, this will be 2.53, this will be 0.72. This is inverse of this matrix into this 10 minus 20. D1, D2 is equal to this inverse into this. This inverse I have determined. This if you simplify, therefore D1, D2 I have determined the unknown displacements. So 1 over AE, this if you simplify, I will get 69.44. Here I will get minus 39.53. This you can check once. So this is my unknown joint displacement. One part of analysis is over. First part of analysis. That's what I was telling. For repeatedly, you have to do the analysis first with respect to global coordinate, because load is in the global direction. That is known. Stiffness matrix you have to generate in global direction. That is from member. From member only, member properties, you have to take member stiffness matrix, you have to generate global stiffness matrix for the total structure as a whole. Take out only that part corresponding to our unknown displacement. From that, you determine the unknown displacement. This is the very first step you have to do. From this, I can determine the member end forces. That's the last. That is the analysis is complete. Each member I have to find out. Again, I will use same kind of force displacement relationship. That is PM. I will take PM is equal to KM into DM. Member displacement. I know the relationship between this global displacement and local displacement. Through that transformation matrix, I know everything. I will find out member end forces. That's all the basic concept of analysis. And third step, to find member end forces. In all the three members, I have to determine. So these member end forces, this suppose whatever is there, that itself you can show it here what we are determining. There are two joints, JN and KN, that have to be very, very careful. J to KN near to for N. That is the direction, positive direction. Whatever we are determining the member end forces, or this is PJ, this is PK. We are determining this end forces only, not this axial force within. That we have to determine afterwards. That is a very simple process. We are determining this PM or this PM I, any member I is equal to, we have, you can say we have, this is AE, axial rigidity of the member, length of the member, PM is given by KM into DM. That's all. Where the DM, again can write if you want, PM to BMI is given by Km of that particular member I, Km of member I into DM. DM is nothing but T into D, S of member I, DS of member I. DS of member I 1, suppose if you take, that is D1, D2, D3, D4. D3, D4 are 0, 0. D1, D2, you have determined. So this is known. Transformation matrix, LM 0, 0, 0, 0, LM. LM for that member 1 is known. Substitute that this Km is AE by L, 1 minus 1. So everything is known. You can find out this PJ, PK. That is the process. For all the members, you can find out. This, if you want, you can say here, this KMI is nothing but PJ, PK. That also you can show it, because it consists of two member forces. So now I will determine that in 5 minutes. I will determine for all the 3 members. So we have completed that analysis of that truss. So you take number 1. I write number 1. Number 1. So PM 1 is equal to PJ and PK of that member. 2 elements like that. So first is Km, that is AE by L. L of the member is 5 into 1 minus 1 minus 1 1. That is Km of 1. Then T of 1. T of 1 is L. L is minus 0.6, M is 0.8, 0, 0, 0, 0, minus 0.6, 0.8. So that is your T matrix. T into ds is dm. So ds is d1, d2. d1, d2, that is again 1 by AE into 69.44 minus 39.53. These are zeros because they already have written 0, 0. So you can simplify this. So this I will do first. This is nothing but 2 by 4 matrix, 4 by 1 matrix. So resulting has to be a 2 by 1. So this is E by 5, 1 minus 1 minus 1, 1. So this into 0.6 into 69.44. What is that value? Minus 69.44. 41.79. So 6 into 4, that you can round it up. Then this is minus, again minus 0.48. Because I have here full simplified value, I wanted to show that calculation. So from minus 0.6 into 69.44.
41.66.
41.664, and like 41.7, then plus 41.7 minus, then 0.8 into 39.53.
31.64.
31.64.
64.
So this I have to add 73.3 minus 73.3. This is 0, 0. Next, this 0, 0, 0, 0. Okay? This is 2 by 4, 2 by 1.
2 by 1.
Okay. Then this is 2 by 2, if I multiply it. And of course, this AE get cancelled, so I can write 1 by 5. So it is 1 by 5 into, this is minus 73.30, it is minus 73.3, this is again plus 73.3. This into this into 0, this into this. So this is nothing but 73.3 divided by 5, that is
14.66.
14.7.
7.
So this is 4 plus 14.7. These are the PJ, that is as I have indicated here. For that member 1, force like this in this direction, right? So it is minus, you have minus means it has to be like this. You watch here. I am getting minus 14.7. This is JN. Minus means this is the direction. When here it is like this, here it has to be this way. This carefully you see how to indicate the member forces. So this is 14.7. This is the direction. It is tension. So this also automatically it will be tension because it is opposite. Here it is plus 14.7, plus means it is in this direction. So this has to be opposite. So this is tension. Is it clear how to find the member end forces from that? Here always make sure they will be equal but having opposite sign. That's all. This is with respect to member 1. So force in first member it is 14.7 kilonewtons. It is tensile. Then we can take member 2 and 3. Member 2 I will determine. Member 3 on same line we can find out. Member 2 that is PM2, that's again two forces PJ, PK of second member that is equal to AE by L, AE by 4. L is 4. So 1 minus 1 minus 1, 1. That is Km into T. T of that member L, M, 0, 0. L is 0, M is 1,
0, 0,
0,
0,
0. Then 0, 0, 0,
1.
1. This is simple when compared to that. Then into ds of member 2. ds of member 2 is again d1, d2 and here it is 0, 0. So d1, d2 is 1 over AE 69.44, then minus 39.53, 0, 0.
0.
So AE cancels, so we can simplify, we get the force in that. So this is 1 by 4 into 1 minus 1 minus 1, 1. Here it is 0, here it is minus 39.53. Correct? Huh?
Yes, sir.
Minus 39.3, this is 0. It is just 39.53. Here it is 0, 0, 0, 0, 0. It is only 0. So that is again, so this 1 over 4, this is
minus
39.53,
plus 39.5.
then here plus 39.53. Of course, this we can divide by 4, you will get minus
9.9.
9.9, huh?
9.9.
And
Yes, sir. 9.9.
or I will say 10,
Minus 10.
minus 10 I will say.
Yes, sir.
This also
Plus 10.
plus 10. So approximately
Yes, sir.
this is minus 10, 10. So you can indicate the force here. So this is minus 10. So minus 10 means the direction is here. You see that direction I have drawn. This is the direction we have marked. Positive direction here. So that is minus I am getting. So this should be reversed. So here also should be reversed. 10.
So, but in previous case, it's also same, right, sir?
Same thing, you can see what is the problem.
Minus
This
40.
is minus. This is minus means it is opposite. So here
Yes.
it is like that. Correct.
Yes.
This also tension. So probably in the other one it will be compression. You can check. Naturally, because it is L and M are minus L and this is opposite to that. But different force you will get. So as per my calculation, that force is 2.2 here. It is compression. These are the force. 14.7, 10 and 2 compression. This is about the complete analysis of truss. Both introduction and a problem has solved. This is the element approach, finite element approach in other words, how to do the analysis. All this we can program it on a computer easily, joint information, how many number of joints, how many number of members, what are the joint coordinates with respect to set of coordinates, what are the member information, A value, all that input. E you can give it automatically, that standard Km, AE by L, 1 minus 1, that it will generate. Then transformation matrix it will generate using that L equals xk minus xj. The coordinates you have in some feed in the computer, so it will compute L and M for each member. It will automatically compute global stiffness matrix. Invert that matrix with everything, give out the output as displacement. Then member and force, again it will come back to your original property of the member. It will compute the member and force as final result.
So it's a element approach.
This is called element approach. This is the only approach you have to do, because I told you truss is a structure made out of only triangle. Arrangement of the members will be in the form of triangles. Otherwise it is not called as a truss. That classification of truss, or what is a truss definition. Truss is, we call that structure as truss only if elements are arranged to form triangle. If it is just rectangle or anything, it is not called as a truss. It becomes a frame, rigid frame. It is not a truss. Hinge on plate zone is stable. If that rectangle or square arrangement zone is stable. So arrangements cannot be just like this. This sort of truss you don't get. Always you should have triangles only. When you have triangle, you have an inclined member. Inclined member only you have to have. Whenever you have inclined, that orthogonal approach, all the members will not coincide with our orthogonal coordinate system. So we cannot follow the system approach with that easy. We cannot follow that, but it will be a tedious calculation, not fast for hand computation. So for hand computation, system approach is easy only if it is orthogonal. Otherwise, that's why we didn't work any inclined like frame problem also there. That's the reason why they are not clearly told in the syllabi. They have clearly mentioned orthogonal, that's the reason. System approach, that's the reason. All these things we have to do. So with this, the matrix stiffness method of analysis completed. Each, frame, and test. All the three types of Dr.SreeKeshava follow. Next, we will take up law of unit.